In this video, I will talk about the compile functions and will show you the most commonly used optimizer and how to select the optimizer that fits your dataset and models. Let's go ahead and get started. Compile function is very important. It is used to configure the models for training. There are three important arguments in these compile functions. The first one is the optimizer, that we will talk about it in this video. And then the second one is the loss functions. And then the final one is the metrics. These figures reveals how we use each of the arguments in the compile functions to set up the whole training, to configure the models for training. Here we have the loss functions. Once the neural network architecture is set up, this is the neural network, the architecture is set up and added into the sequential model. Samples here are forward propagated to the corresponding estimate y hat will be calculated based on this training model. And then the loss function is then applied to estimate the loss value between the true labels and then the predicted value, the estimate y hat. And then we calculate the loss value. Now and then for the optimizer, based on the loss value, the optimizer will backward propagate and calculate the gradient with respect to the W and by and base parameter, that is the weight and also the bias parameter. And then the training will stop either when the maximum number of epoch in fit function is reached, or a monitored quantity with the function has stopped its improving. That means the monitored the quantities or the loss rate cannot further improve. There is a early stopping functions that we will introduce you to avoid the overfitting problems. Now, these will form a closed loop, just like what I mentioned. The maximum number of epoch in the fit functions is the way to determine how many times we continue to make this loop. And you can see that the metric function doesn't appear here. A metric is an additional evaluation function that is just used to judge the performance of the models. Metric functions are very similar to the loss functions, except that the results from evaluating a matrix are not used when training the models. Therefore, any loss functions can also be used as a matrix. However, you can see that the metrics are not included in this diagram. Therefore, in this diagram, loss functions is here to help us to do the forward propagations, and the optimizer is here for us to help us to do the backward propagations and continues to improve the training. The main reason is because this is very difficult for us to judge the performance based on these loss value. Therefore, we want to have another parameters or another functions to help us to understand how good or how bad our models are performing. Therefore, sometimes an extra metrics such as accuracy or mean absolute errors are used for additional evaluations. Now, let's take a look on the commonly used optimizer. Almost all popular optimizers in deep learning are based on gradient descent, which estimate the slopes of a given loss functions and update the parameters towards a supposed global minimum. There are three different types of gradient descent. The first one is the batch gradient descent or the vanilla gradient descent. That means the entire database are used to compute the gradients for the cost functions. And then for each iterations, And then the gradient descent will try to update the parameters based on the entire data set. And the other one is the stochastic gradient descent. In this case, a single sample is randomly picked and used to compute the gradients of the cost functions. And then for each iterations, the gradient descent will update the parameters. The final one is the mini batch gradient descent. This is a variation of the stochastic gradient descent. A mini batch of the samples is randomly picked, and that means this is a subset of the entire data set, and used to compute the gradients of the cost functions for each iterations of the gradient descent, and then updates the parameter. The problems of the batch gradient descent or vanilla gradient descent is that because it takes the entire database into considerations for the training. As a result, it will slow down the training, and the training will be extremely slowed. On the other hand, the stochastic gradient descent, because it only takes one sample, therefore, the training will be very fluctuated. In that case, it's very difficult for us to judge whether or not we reach a global minimum. Therefore, very often, we will use the mini batch gradient descent to take a balance between these two types of gradient descent. Let's take a look on some commonly used optimizer. Let's denote the parameters equals to W, the gradients equals to G, the global learning rates equals to alpha, the time step equals to time t. And we have the first one that I would like to introduce is the stochastic gradient descent. These SGD functions is, although it's called the stochastic gradient descent, is actually applying the mini batch gradient descent. The optimizer estimates the directions of the steepest descent based on the batch size defined in the fit functions and take a step in that directions. However, the step size is fixed. That means even though it got the right directions, the step size is fixed. Therefore, SGD can quickly get stuck on the plateau or local minima. And of these rules, you can see that just simply use the global learning rate here, the alpha, with the times the gradient to control how much that we would like to update the parameter. Just like what I mentioned, these alpha and these gradient descent, the step size is fixed. Therefore, it's very easy for it to get stuck on the plateau or the local minima. In that case, we would like to introduce a momentum to these SGD functions to make it accelerate in the directions of the constant descent. That means if it predicts it correctly to the global minima or the local minima, it will speed up the training. It will speed up into that directions with the momentum. The acceleration is defined by the momentum beta, which is less than 1, which helps the model escape the plateau or escapes the local minima and make it much more easier to escape from that problem. And you can see that the update rule, instead of just use the learning rates multiplied by the gradients, now we multiply by a velocity. And this velocity is controlled by the momentum term beta, and of course is controlled by the gradients. If we set the beta equals to 0, the first equations will just get the gradient t, and as a result, it will be same as the original SGD. So if we set the momentum terms equal to 0, and then the SGD will be without the momentum. In Keras, the SGD functions combines the SGD without and with the momentum. So we can just simply set this momentum value. When the momentum is larger than 0, SGD functions will update the gradient with the velocity equations here. Therefore, the hyperparameters beta here must be within 0 and 1. There are two challenges when we are applying the SGD functions. The challenge mainly coming from the learning rate. First of all, is that the learning rate has to be set in advance, and they depend heavily on the types of the models and also the problem. Another problem is that the same learning rate is applied throughout the entire training. In that case, if the data is sparse, it's better to be updated the parameters at different rates. And Ada grade make use of the adaptive learning rate to address these issues. It scales the learning rate alpha for each parameters based on the square root of the inverse sum of the squared gradient. That is based on these two equations here. So in short, these methods will scale the sparse gradient's direction up, which allows for larger steps in such directions. That means when it saw there a sparse gradient, it will just step up in that directions and results a faster converge into the problems with sparse features. And because of that, you can see from the update rule, now the learning rate is controlled by the sparse features and make it to learn it adaptively. Ada gradient's main problem is that its accumulations of the square gradients is in the denominator. The accumulated sums keep growing during the training. This in turn causes the learning rate to shrink and eventually becomes very inefficient at the point that it is no longer able to acquire additional knowledge. To solve this radically diminishing learning rate, we will introduce you the RMS prompt. RMS prompt scales the gradient in a less aggressive way. Instead of taking the sum of the square gradients, it takes a moving average of the squared gradient. And also, RMS prompt is often combined with the momentums, which helps the model escape from the plateaus, escapes to the local minima, and make it less susceptible to getting stuck in local minima. In its nutshell, RMS combines the benefits of the Ada grade and also the benefits of the momentum. And as a result, RMS prompt is extremely popular nowadays. There is another very recent famous optimizers called Adams. Adams actually combines the Ada grades, RMS prompt, and also momentum methods into one. And the directions of the steps is determined by the moving average of the gradient. And then the step size is approximately upper bounded by the global step size. And also, furthermore, each dimension of the gradient is rescaled similar to the RMS prompt. In that case, it also takes the advantage from each of the methods that I mentioned before. One key difference between the Adams and also RMS prompt or Ada grade is that the moment estimates MV are corrected for bias towards 0. Therefore, Adams is very well known for achieving good performance with very little hyperparameters tuning. Therefore, if you compare the Adams to RMS prompt, you can see that there will be beta 1 and beta 2 instead of just one beta, because there is a moment estimates are introduced in the Adams. That is used to correct the bias towards 0. And that means it's much more easier for them to achieve good performance without tuning so much in the hyperparameters. As a rules of thumb, if the input data is sparse, then we much more prefer to use the adaptive learning methods, because it will probably likely provide a better converge and also better result. However, if you have the resources to find a good learning rate schedule, SGD with momentums is a very, very solid choice. In that case, if you have enough computational resources and you do not mind to have a very slow learning rate schedule, and SGD momentums is also a very good choice. And RMS is an extension of Ada gradients that deal with its radical diminishing learning rate. Therefore, in general, if we know that the data is sparse, we will just use the RMS pops instead of the Ada grade. Adams adds the bias corrections and momentums to RMS pops, and its bias corrections help Adams slightly outperform the RMS pops towards the end of the optimizations as the gradients becomes sparser. So insofar, Adams might be the best overall choices for the adaptive learning rate methods. However, if just in case if your dataset or if the gradients do not become sparser at the end, the performance of Adams and the RMS pops would be quite similar. Therefore, Adams and RMS pops are very good starting points for approaching any problems. In this video, I just gone through the compile functions and showed you the most commonly used optimizer and why Adams and RMS pops are more popular and preferable in most of the problems. In the next videos, I will provide you more details about another argument in the compile function, that is the loss functions. See you in the next video. Bye-bye.